Professor R. Asokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series intended for the BSc Honours Physics students. We have been going through a course of lectures on interferometers, and especially the Michelson interferometer. In the last lecture, we saw the construction and the working principle of the Michelson interferometer as well as its varied applications. And in this lecture, that is lecture number 24, the contents will be as follows: review of the experimental setup and its working, connection between wavelength of the source and the distance through which the mirror is moved, formation of circular and localized fringes, standardization of meter. Now, this picture again shows the Michelson interferometer. This interferometer is of immense significance because of the fact it has got wide variety of applications. I covered the following applications in the last lecture, namely this interferometer can be used to determine the wavelength of a monochromatic source of light, the thickness of a thin transparent film, and the refractive index of a gas enclosed in a container. And again, most important thing is the standardization of meter. So, this instrument, its working principle, all these things have been dealt with in a greater detail in the last lectures. You have got a glass plate here, another glass plate called the compensating plate, and these are things that you have seen. The two important things which are to be remembered are, if the two mirrors are mutually perpendicular to each other, then you will be getting circular fringes, right? That is one thing that you should be remembering from the last lecture. And the second thing is, one mirror is a movable mirror, the other is a fixed mirror. The two mirrors are perpendicular to each other, you will be getting circular fringes. Then, when will you get localized or straight fringes? If one of the mirrors is making a slight angle of inclination, then you get a air wedge. This will produce what are called the localized fringes. So, you get circular fringes. When do you get circular fringes? If the two mirrors M1 and M2, one of them is fixed, the other is movable. If they are perpendicular to each other, you will be getting circular fringes. Then the second thing is, if the movable mirror is slightly inclined, it makes a slight angle of inclination, then the path that the light ray has to travel through will become it will encounter a wedge-shaped, air wedge-shaped film. So, it will result in the straight bands. You will have bands like the, here one of the mirrors will be like this. One mirror M2 prime will be having a slight angle of inclination leading to the straight fringes. Now, we saw in the last lecture the measurement of wavelength. I have the slide once again because this lecture contains a lot of intricate ideas. Now, as the mirrors move through a known distance d, let me redo the same thing. The mirrors move through a known distance d, that is a movable mirror. The number of fringes disappearing at the center is counted. The fringes which are disappearing at the center is counted. So, when you get circular fringes, I told you that you will be having darkness. The condition I gave for the bright or dark fringes or 2d cos theta plus lambda by 2 will be equal to m lambda, this kind of the conditions you know. So, if the path difference is lambda by 2, then you get darkness. On the other hand, if the movable mirror is moved through lambda by 4, the mirror is moved through a distance lambda by 4 means the path difference will be, how much will be the path difference? If the mirror is moved through a path lambda by 4, the light beam has to go and come back because twice the distance through which the mirror is moved. If it is moved through lambda by 4, 2 into lambda by 4 will be lambda by 2. So, if the mirror is moved through lambda by 4, the path difference will become lambda by 2. So, if the path difference is lambda by 2, what do you mean by saying that the path difference is lambda by 2? If lambda means, the path difference lambda means what? Crust meets a crust or a trough meets a trough. If the path difference is lambda by 2, a crust will meet a trough. Therefore, when you have got darkness here, that will become bright. So, lambda by 2 means you will be having the condition for darkness. From the condition of darkness, you go to the condition of brightness, and so you get a bright region at the center. So, this is one of the important points. And the second point is, I told you in the last lecture, when we want to determine the thickness of a thin glass plate using the Michelson interferometer, when you interpose a thin plate, the fringes are getting shifted. The shift in the fringes cannot be measured by looking at the yellow background, because when you use a sodium vapor lamp, the fringes will be yellow in color, bright and dark, bright and dark. There will be shift, but how many fringes have been shifted you cannot determine. Therefore, what do? You use a white light. You use a white light, the center of the white light will be a dark band, the central will be a dark band, a dark line, and the dark line will be used as a reference line to determine or to measure the number of fringes which have moved through because of the thin plate being introduced. Therefore, let me ask you the question. Now, what is the wavelength of sodium vapor lamp? The wavelength of sodium vapor lamp, all of you know, it is 5893 into 10 to the power of minus 10 of a meter. That the wavelength is so small, right? Now, you know this wavelength can be determined using the Michelson interferometer. How do you measure the wavelength? The wavelength lambda of the sodium vapor lamp is given as 2d by n. That is what we have seen in the last lecture. This is an important slide. This is the crux of the problem that we are going to deal with today. It lies at the last line, namely the wavelength lambda. I told you in the contents, the connection between the wavelength and the d is the distance through which the mirror is moved, the movable mirror is moved. You know, one mirror is fixed, the other is movable. The movable mirror is moved or shifted through a distance d. When it is moved through a distance d, n is the number of fringes that are getting shifted. So, the point is the distance d through which the mirror is moved will give rise to a shift in fringes. How many fringes? N is the number of fringes through which they pass through the crosswire, right? When the mirror is moved through a distance d, n fringes will be crossing, will be going through the crosswire. So, lambda is the wavelength. So, the question that I am asking is, if d lambda n, they are connected, then how many fringes are to be shifted? Or I may ask the question the other way around. If a small distance, what will be the magnitude of d? D will be, say, 0.1 millimeter. D is the distance through which the mirror is moved. It is 0.1 millimeter. If this 0.1 millimeter gives rise to a shift of 10 bands or 10 fringes, then what I would like to do is, I want to know if the mirror is moved through 1 meter, how many fringes would have been shifted? Remember, my question is, if the movable mirror is shifted through 1 meter, when it is 0.1 millimeter, 10 fringes are shifted. If it is moved through 1 meter, can you move, you can visualize, you can see the Michelson interferometer, which is kept on the table, equipment in the lab. So it will be in few centimeters. So you cannot have, you cannot move the mirror by such a distance like 1 meter. If you move one of the mirrors through 1 meter, then what will happen? You won't be getting interference bands at all. When will you have interference bands? The bands will be obtained only if the wavelength of the wave and the distances which you are talking about, a few millimeters of distances which are through which it can be moved, or centimeter, then only you will be getting stable interference fringes. At the maximum, the path difference between the two waves, or in other words, the distance through which one mirror is shifted from the other mirror should be of the order of 10 centimeters. What I mean by this is, look at the diagram once again, and I have the, one mirror is here, the other mirror is here, right? There are two mirrors. This is a mobile mirror, this is a fixed mirror. The distance between these two mirrors are made to be equal to one another, and again they are mutually perpendicular to one another. Then you will be getting circular fringes, and the distances are equal, right? From this point here, from here to here, and here to here, the distances are equal. If it is displaced by 1 centimeter, still you will be getting the circular rings. 2 centimeter also will be getting circular rings. So how much your mirror, the mobile mirror, can be shifted or moved? At the maximum, it can be moved by a distance 10 centimeter. What I mean is, the distance between this mirror and this point, and the distance between this point and the mirror M1. So the distance between this point and M1 and the distance between the same point and M2 should not differ by a few centimeters. At the maximum, 10 centimeters. You cannot have 1 meter. What I want to do in the whole today's lecture is meant for standardization of meter. Standardization of meter means, what is 1 meter, or how can you standardize a meter? Where do you have meter? Meter is kept in Paris, right? The meter, as we understand today, is kept in the Institute of Measurements Standards. It is kept in Paris. That is where you say it is 1 meter, right? It is, the credit goes to Charles de Goulamy, who defined meter. You have heard of Invar, Elinvar, and so on. So you have got 1 meter that is kept in Paris, that is 1 meter. So you cannot move the mirror M2 through a distance by 1 meter, then you won't be getting interference pattern at all. So the distance between this and this, and distance between M1 and this point, M2 and this point, they should not differ by more than 10 centimeters. Now therefore, I want to know, if I move it through 1 millimeter, I get 10 fringes moved. So I want to know what is 1 meter. So, or how many fringes should be shifted in order that it corresponds to 1 meter, right? Corresponding to 1 meter, 100 centimeters, the number of fringes which will be shifted will be enormous, and it is impossible to move it through 1 meter. If you let us have a break at this point, then we will come back to interesting problem after the break. Welcome back to the break. As I mentioned just now, this lecture is centered around what is called standardization of meter. What do you mean by standardization of meter? You want to know what is the meaning of 100 centimeters. How do you say this particular length is 100 centimeters? I want to finally have an expression. Suppose I use cadmium vapor lamp, the red line of the cadmium vapor lamp. It has a wavelength, right? So the sodium vapor lamp has got a wavelength 5893 angstrom unit. 5893 into 10 to the minus 10 meters. That is wavelength. Wavelength is this much, right? And I want to finally have an expression. 1 meter is equal to so many lambdas. Hope you understand the problem. You know, what is lambda? Lambda is 5893 angstrom unit, or 5893 into 10 to the power of minus 10 of a meter is lambda. And 1 meter is equal to how many lambdas, or how many waves, how many millions of waves, or how many lakhs of waves will be equivalent to 1 meter or 100 centimeter. Okay, this particular point should be very clear to you. You know the wavelength of sodium vapor lamp 5893 into 10 to the power minus 10 of a meter. That is wavelength. Okay, it is immeasurably small. Your meter is something which is remarkable, which is so very big. And the question that I am asking is, how many waves you can have in 1 meter? So finally, when the lecture is over, I will show for a cadmium red line in 1 meter how many lambdas will be having. You know, wavelength is something which varies from visible light. The wavelength varies from 4000 to 7000 angstroms. If I take sodium vapor lamp, it is 5893 angstrom unit. In 1 meter, how many 5893 into the minus 10 meters are there, right? How many lakhs or millions? So finally, I have to write an expression, or I have to determine using the Michelson interferometer. I have to determine 1 meter is equal to so many waves. You know, if I move the mirror through lambda by 4, it is equivalent to introducing a path difference of lambda by 2. That is lambda by 2. Lambda is the wavelength, right? Lambda by 2 will give rise to, from bright band, you go to a dark band, or from a bright ring, you go to a dark ring. If it is integral multiple of lambda, into lambda by 2, you go to lambda, then what do you get? From bright, you go to bright. From lambda by 4, movement of the mirror is equivalent to introducing a path difference of lambda by 2. So from darkness, you go to brightness, right? Again, you go to darkness. Again, you go to brightness. From brightness to brightness, how much you have to? From brightness to brightness means what? So it is 0, lambda, 2 lambda, and so on. So the condition for constructive interference is lambda or 2 lambda. The path difference should be equal to lambda, 2 lambda, and so on. So if the path difference is lambda, then you will go from brightness to brightness, right? The path difference lambda means what? The mirror is moved through a distance lambda by 2. The mirror is moved through a distance lambda by 2. This is the mirror. If the mirror is moved through a distance lambda by 2, then you will go from the bright ring to another bright ring. Okay. Now, you know what is lambda. Now, the question that I am asking is, how many lambdas are to be moved? How much distance the mirror should be moved? Suppose the other way around, if you move the mirror through 1 meter, how many times from bright you get a bright, right? From bright you get a bright ring. The distance moved is lambda, right? The distance moved is, the path difference is lambda, and the distance moved of mirror is lambda by 2. From brightness to brightness, the path difference is lambda. You know, lambda, 2 lambda, they will give rise to constructive interference. You get brightness, and again brightness means the path difference is lambda. The mirror is moved through lambda by 2. Now, again you move the mirror through lambda by 2, you will get again brightness and so on. Okay. So, how many times you have to have brightness in order that corresponds to 1 meter? That is the question that you have in you should be having in mind. And the expression, as I told you, the point is for a displacement that is experienced by mirror, then a certain number of fringes, n number of fringes would have moved. So that is another point that should be, that is important point, right? The experiment to measure the standard meter that is kept in Paris in terms of the wavelength of the cadmium red line was first performed in 1895 by Michelson and Bennett. Now let me post this particular point. Having known the connection between the wavelength of a monochromatic source and the distance through which the movable mirror is moved, that is the expression that I showed just now. Your D and N or D and lambda, they are connected. That is the expression that you made use of for the determination of wavelength of the monochromatic light. That is the expression, whatever I showed is was used in the last lecture for determining the wavelength of a monochromatic source. Okay, the lambda is the wavelength of the monochromatic source, right? So there is a connection between these two things. So that indicates when you got small d, if small d is equal to 1 meter, how many fringes would have moved? The question is, if small d is made equal to 1 meter, suppose the movable mirror is moved through 1 meter, how many fringes would have been moved? In principle, you cannot move the mirror through 1 meter because the fact movement by 1 meter will completely destroy the interference pattern. The interference pattern will not be visible at all. That is another problem. So having known the connection between the wavelength of a monochromatic source and the distance through which the movable mirror is moved, it should be possible to measure distances by counting the number of fringes moved. So I have given the headline, heading as measurement of distances using Michelson's interferometer. The distance between two stars can be measured using Michelson interferometer. Similarly, the distances can be measured. So what is 1 meter? Meter can be measured. Okay, that is our whole aim is how to define a meter in terms of lambda, right? Wavelength lambda is in order of 10 to the 10 meter. So obviously meter is there. Standardization of meter, the experiment to be performed will be as follows. The Michelson interferometer is used light from a source S after passing through a lens L incident on a glass plate A, as will be shown in the diagram to come. One portion of the light is reflected. You see a source here, light coming from a source after passing through the lens L is incident on a glass plate kept at an angle of inclination 45 degrees. A portion of the light will be reflected and moves towards the mirror M1. The mirror M1 is a movable mirror. It is resting on a platform. There are finer screws using which the mirror can be moved either towards the plate A or away from the plate A. So the mirror can be moved. Not only it can be moved, the angle of inclination also can be slightly changed. Why should you change the angle of inclination? Need not be exactly perpendicular to the light beam. It can be slightly inclined also. If this mirror and the other mirror that you had as M2 in the case of the Michelson's normal experiment setup which I showed earlier, if they are perpendicular to each other, then you will be getting circular fringes. You make one of the plates to be slightly inclined, then you get straight bands. Okay, that also is possible. There is a provision given to the table here on which the platform or the table on which the mirror M1 is kept. M1 can be moved either towards A or away from A, and also it can be inclined. Whereas M2 is the one that is fixed. The mirror M2 is fixed. Okay, the mirror here M2 corresponding to mirror M1, the M2 is here, M2 is fixed. So what I would like to tell you again, the light coming from the source, it is partly transmitted towards the movable mirror M1 and partly it is transmitted. Here it is reflected, it is transmitted and it is incident on another glass plate, and then it is getting reflected and goes to the mirror M2, which is a fixed mirror. And what are this small m1 and m2? small m1 and small m2, it refers to, or it is called as a etalon. Etalon is a pair of mirrors through which light can be reflected. You know, it is a pair of mirrors separated by different distances. This is the smallest etalon I am showing. I will tell you why you are using etalon. I told you some time back, the mirror that you have got in the Michelson interferometer can be moved only through a few centimeters. If you are moving through 20 centimeters, then the path differences will become very large. You won't be getting the interference pattern at all. So therefore, the etalons are used. I will tell you what is an etalon. The other part of the beam, after being reflected by the mirror M, falls on the mirror M2. The M2 is a fixed mirror M2, a fixed mirror M2, and the shortest etalon, which consists of two mirrors. This is called the etalon, which consists of two mirrors M1 and M2, separated by a distance like 0.390625 millimeter. The one that was originally used by Michelson Benedict is was having the distance separating the two mirrors M1 and M2 was of the order of 0.390625 millimeter. That is called a etalon. In the experiment which is performed normally, or which was performed earlier, you have the first etalon, the shortest etalon. The distance separating these two is very small. The next etalon will be having the distance separating the two mirrors twice this value. Instead of 39 or 4.4 millimeter, it will become 0.8 millimeter. And the next one will be 2 times 0.8 millimeters. So every etalon will have its distances separating the two mirrors, they get doubled. As many as 10 etalons are used in the experiment which is conducted to determine to standardize the meter, or to determine how much lambdas are there in 1 meter. So the final thing is 1 meter will be containing how many millions of lambdas, how many millions of waves. So etalons are used as the movable mirror, cannot be moved through a distance more than 10 centimeters. As I told you, if you move through 10 centimeters, more than that, then you won't be having interference pattern at all. Let me now pass on to the summary of this lecture, the working of Michelson interferometer and its use in determining the wavelength of a monochromatic source is briefly reviewed. As wavelengths which are in the order of 10 to the power minus 10 meters can be measured, it should be possible to measure even meters. Lastly, to introduce larger path differences, etalons are used. Let me now pass on to the question session. 1. Recall the relation connecting the wavelength of a monochromatic source and the distance through which the movable mirrors shifted. Question number 2. When do you get circular fringes and straight fringes? Question number 3. What is an etalon? With this, we come to the end of lecture number 24, and in the next lecture, I will discuss in detail one of the very difficult problems that we are facing, namely getting a connection between a meter or expressing meter in terms of millions of the wavelengths of a given monochromatic source. So 1 meter consists of how many waves? That is the final result that we have to obtain. That we will see in the next lecture. Thank you.